So, time to start. It's a real pleasure having with us Cristina. She's going to talk about basically the kind of things that she has been doing since the PhD thesis, basically. You did a PhD here, so for most of us, she's a well-known researcher. She did a PhD here, postdoc then in the UK, returned, got a Marie Curie, and now is a Ramon y Cajal Fellow. So, and she's really a renowned expert in the topic she's going to talk about. It's basically a review that she gave, she has just told me in a meeting, and then it's like slightly biased towards the type of work that she's doing. So it's a kind of global review focus on what she's doing. So stop here and let you talk.
Thank you. Okay. Well, hello everyone. Thank you for being here in this cold morning. So I decided to give this seminar, as Jorge said, because I had to prepare a review for a conference, and also I gave recently a seminar in Rome. And when I came back, I thought, when it was the last time I gave a seminar at the IAC, and I was searching in the archive, in the IAC Talks page, and it was in 2011. So it has been a while. I was actually scared of staring at me in the screen at the time, because I have changed quite a lot. So well, I decided to tell you about the work that has been done regarding nuclear obscuration in AGN. So the talk would mainly be about AGN obscuration, about the torus, the inner AGN structure, because there are amazing results coming from both the infrared range, but also from the sub-millimeter, thanks to ALMA. And I will talk also at the end of the talk, if I have time, about my more recent work on AGN feedback, also using the infrared and the sub-millimeter. So, because not all of you work in AGN, and even for us, AGN researchers, it's always good to remind ourselves why studying AGN is interesting. And well, like let's say 20 years ago, people study AGN just because they were, well, interesting by themselves, but not because people thought that they had any key influence on the galaxies they inhabit. But this has changed quite a lot in the last years. Actually, and this is partly because AGN, nuclear activity, is no longer understood as something static, like active galaxies are active galaxies and they continue like that forever, and the same for star-forming galaxies, which are not non-active. But instead, the nuclear activity is considered as a relatively short active phase in the life of a galaxy that can be very short, according to the last simulations and also to some observations, as short as 0.1 mega years. This is nothing compared with galaxy time scales. For example, if you think in the time scales of mergers or bars, which are, I don't know, 1 to 3 giga years. So 1 or 0.1 mega years is nothing, it's just a moment in the life of a galaxy. Of course, it can be a bit longer, especially in the case of quasars. But the idea is that if there is a gas supply towards the supermassive black hole that we have in the center of the galaxy, and the conditions are the ones required to trigger the activity, then the Eddington ratio increases, and we can observe a galaxy as an AGN. And when the fuel supply stops, then the Eddington ratio decreases again, and we see a galaxy as a normal galaxy. And as we see, especially from simulations, this can happen even several times, like I said, in the lifetime of a galaxy. So perhaps all galaxies, or at least all massive galaxies hosting supermassive black holes, can be active at one or several times during their lives. Another reason for the increased popularity of AGN amongst galactic studies is the AGN feedback that I'm sure you have heard about. So the feedback is the effect that the AGN has on the host galaxy. And this feedback can happen in very different ways. So for example, the AGN can remove the gas or heat the gas available to form new stars and then quench star formation. But also it has been observed that in some cases the AGN does not produce quenching, which is what we call negative feedback, but it can have the opposite effect. So for example, if the AGN just perturbs the gas that is surrounding, it can enhance star formation. And we found some examples in certain galaxies of positive feedback, so the AGN enhancing star formation because the conditions are favorable for having a star formation. So this AGN feedback, in particular the negative feedback, is expected to shape the M sigma relation, so using this, all these scaling relations that we are aware of, and also the simulations, the models and the simulations of galaxy formation require the AGN feedback for explaining the observed number of massive galaxies in the luminosity function. So for example, in this plot here, which is from a semi-analytical model, I think, we have here the blue dots and squares are the observations. This is a luminosity function. And as you can see, the observations are well reproduced by the model when they introduce AGN feedback. And when this feedback is not introduced, then the number of massive galaxies increases and does not coincide with observations. So simulations need this negative feedback, and this is why we are so interested in finding it, because so far it's a bit controversial, as we will see later in the talk. But like I said, in some cases we are finding examples of the opposite, of positive feedback. Something that we have learned during the last years as well is that if we want to understand the complexity of AGN and of AGN feedback in particular, we need to look at different galaxy scales, because feedback takes place in different scales of the galaxy, and also to look at different gas phases. Normally we look only at ionized gas, for example, but we need to look at the molecular gas, at neutral gas, to fully understand what's going on. Because in terms of scales, and also of tracers, the feedback, the outflows in particular, propagate from the very central region of the AGN, from the central parsec, and this is something that we would be able to observe, for example, in the X-rays, because this is very energetic phenomena, through the surrounding medium of the galaxy, going from scales that go from the first parsec to several kiloparsecs. And in some cases, the outflows or the jets in this case exceed the boundaries of the galaxy, and we observe things on scales larger than 10 kiloparsecs, for example. So in this talk, I'm going to concentrate on these scales, going from the central parsecs to the central 1 or 2 kiloparsecs of the galaxy. Like I said, first I will focus on AGN obscuration and then a bit on AGN feedback. Okay, so this is more or less the structure, the nuclear structure of AGN as we understand it today. This is from a review on nuclear obscuration that we published in 2017. So we are talking about a tiny region in the center of galaxies. As you can see here, for example, this is Circinus galaxy. This is actually the center of the galaxy, a circum-nuclear ring of 200 parsecs diameter, and this is the narrow line region. And we are looking at something, like I said, tiny in the center of the galaxy, and it would look in a very cartoonish view as something like that. No? So we would have the supermassive black hole in the center and the accretion disk, surrounded by the broadline region clouds, which are inside the sublimation radius, so we don't have dust in here, only gas. And beyond the sublimation radius, we start to have the torus clouds, which are made of gas and dust. This is in the equatorial plane, but in the polar direction, we have this narrow line region, the cones that we observe in the HSD images, for example, very nice ones. But on smaller scales, as I will show you in a few slides, there are also evidences for polar dust, which is coexisting with the torus at the same scales, and it might be very important in terms of the infrared emission of AGN. And also something that I will refer to during the talk is this circum-nuclear disk CNGs, which go from 10 to 100 parsecs in the case of intermediate luminosity AGN, like Cipher galaxies, for example. And this is basically the molecular gas reservoir of the AGN and also of the central part of the galaxy. Okay, and if we want to study this circum-nuclear environment of AGN, the central parsecs, because there is a lot of dust, we need to look at the infrared, because in the infrared we see there is the dust absorbs the optical and UV photons that are produced in the accretion of matter into the supermassive black hole and re-emit them in the infrared. So we get to see, to study this, the dusty structures that are re-emitting this radiation. And in AGN, nuclear dust is mainly composed of graphites and silicates. So some of you maybe have seen this slide because I have used it before in other talks, but I think it's very illustrative of what we need to do if we want to study the very central region of AGN. Because we need angular resolution, so we need to go to large telescopes. This is going to change with the James Webb, of course, because it's going to produce the same angular resolution that we can get in the mid-infrared from the ground at even higher sensitivity, so this is going to be great. But until James Webb, the best thing we can do in terms of angular resolution is go to large telescopes like the GTC. And I'm going to show a comparison between a set of images observed with Spitzer and then with the Canary Camp in the GTC. So this is a sample of luminous infrared galaxies observed with the Spitzer with very low angular resolution, and then the same targets observed with an instrument like Canary Camp. So you can see that we observe a level of detail that it's impossible to achieve with the resolution of a Spitzer. And this is what we need to do if we want to isolate the most, as much as possible, the nuclear emission of AGN. So for example, if you want to have an idea in numbers for a galaxy at 30 megaparsecs, with Spitzer, our resolution element with IRAC at 8 microns would be of 450 parsecs. So we have circumnuclear rings, a lot of star formation going on, contaminating our nuclear measurements. And in the case of Canary Camp, we will be talking about the inner 45 parsecs, so dominated by the nuclear emission, by the emission of the torus, as we will see. So this is how our view of the torus, of the nuclear obscuration of AGN has changed in the last years, thanks to infrared observations. In this case, from the VLTI. In Chile, and also from the sub-millimeter point of view, thanks to ALMA, where we are looking at colder dust within the torus. Basically, from the interferometry results in the mid-infrared, we see that for some galaxies, for the most nearby galaxies that have been observed, because the problem with the VLTI is that you are limited to very bright objects, so they can only observe like 20 galaxies, and only I would say maybe 6 or 7 at the sensitivity required to derive the results with a high confidence. But this is my opinion. So they are observing that, for example, this is a Circinus galaxy, a very nearby intermediate luminosity AGN. In addition to the disk, which is what we would, it would correspond to the torus, let's say, we also have a polar emission in the perpendicular direction. And the surprising thing is that this, so the interferometry guys said that this polar emission in the infrared, it's dominant over the emission of the torus. So the polar emission in the mid-infrared would be more important. So if this is true for all galaxies, the work that we have done in fitting infrared spectral energy distributions with torus models only would be wrong, because we are using a too simplistic approximation. But it's soon to be able to say that, because this is something that we only know so far for I think 6 galaxies. So we need more numbers to be sure that this polar emission is really dominant in the infrared or not. In the case of ALMA, as I will show later, we have been able to resolve the torus for the first time. So a few years ago, we never saw the torus. The only thing that we could do, like I said, was to feed the infrared spectral energy distribution with torus models to try to infer the properties of the torus. But now with ALMA, we see this tori, not only for NGC 1068, which was the first one, but for a few galaxies now, and I will show you the results. So before that, this is how so I mentioned observations before, but this is how the models have also changed to try to accommodate these new observations that we have. So we started with the smooth torus of Pierre and Krolik in the early 90s, and the picture has evolved quite a lot. So first, we moved to the clumpy models. So we saw that the medium couldn't be homogeneous because it didn't reproduce the observations that we had at the moment. So we went to a clumpy distribution of the dust in the near environment of the AGN. And now, because of this polar emission that I was telling you before, the models are incorporating these polar structures, which is an outflowing wind, as we will see, driven by radiation pressure on dust. And we have different sets of models trying to incorporate this polar dust from a physical point of view. Sorry, say the last. Yeah. I would say no. So in principle, no. This has appeared. Well, let me say that, for example, these models, the WADA models, this is from a Japanese group. They were starting to talk about these polar structures, I think, because they appear naturally in the simulations, even before we knew about the polar dust, because the first models are from 2012 or even before. And it's true that the importance of the polar component, I think I first saw it in 2013. So yeah, so in this case, they probably anticipated a bit what we now see in the observations. So something that it has changed from the observational point of view, like I was saying, is that we changed our view of the torus going from homogeneous to clumpy. This is something that is now well established. And for example, we know it from different types of observations. And here, for example, I'm quoting the X-ray observations because I think this is a nice independent test for clumpiness of the torus. Basically, the X-ray people look at the same AGN doing follow-up observations, and because what they see is changes in the column density, so you get to see if it's constant or if it increases and decreases. And depending on the time scales of these changes in the column density, they can explain it as due to passes of the clouds in the broadline region or in the torus. So in the broadline regions, we would be talking about transients of days, perhaps, or hours. And in the case of the torus, we see variations of months, typically. So this is a nice test, what we have from the X-rays. And this is from a paper that was published in 2014, precisely. I think it was the paper doing the largest compilation of column density variability in nearby AGN. And they detected these occultation events, or changes in the column density for a few AGN, like 10 or something like that, that were observed for several years, like I said. And this is a movie that they prepare, like to try to illustrate what they see. So what you see in gray would be the torus clumps, and in color are the VLR clouds, and also there is a jet in the polar direction. So when a cloud in the torus intercepts our line of sight, then we would see the AGN as obscured in the X-ray. So this is the idea. from the, so with instruments like Canary Cam on the GTC and also other instruments in the Gemini telescopes, we have studied the mid-infrared emission of nearby AGN. This is from the thesis work of my former student, Ismael Garcia Bernete, who finished his PhD, and he observed a sample of Cipher galaxies with Canary Cam in the mid-infrared, and something that we saw is that the mid-infrared emission is normally dominated by the point source, but we also detect extended emission surrounding this nucleus, which is much fainter than the nuclear point source, and typically extends over 400 parsecs or so. But in principle, yeah, this emission is quite punctual. And something that we have seen also, this is not, before when I was telling you about the polar emission, I was referring to VLTI data. So we are talking about the inner 10 parsecs maybe, or even less than that. But from the ground, not with interferometry, but with direct imaging and spectroscopy, we see that in some galaxies in which we observe this extended emission in the mid-infrared, this emission is elongated in the polar direction, and this could be a hint also of the importance or not of this polar component to the mid-infrared, even on larger scales, so on scales of 100 parsecs, let's say. And this is from interferometry. This is models. One problem of mid-infrared interferometry is that here we are not seeing images. This is a model to reproduce what they see in the UV plane. But now this is going to change with Matisse. Matisse is a new instrument that is going to the VLTI, and it's going to produce images. So no models anymore, but we will be able to see if this is real or not. And I think they are doing the commissioning now, and soon there will be a press release probably on something related to this. Because in this conference I went to, they said that they had promising results that they couldn't tell us at that moment. Yes? The fraction of type 2s, of Cipher 2s, which show this polar emission in the VLTI or in the ground base. In the VLTI there are only 6 sources with confirmed polar emission, and I think 4 are Cipher 2s. I think there are only 2 Cipher 1s, I think. And in the case of the mid-infrared imaging, normally they see it in the type 2s because it's easier to see the extended emission in type 2s than in type 1s, because in the type 1s they are dominated by the point source. I don't hear you very well, but if you mean how important is the mid-infrared emission over the torus emission, the polar emission versus the torus? Yes. Yeah, for example, in this paper, I think they had a lot of AGN observed with this year in the VLT, and only for, I don't know, 15 out of 100, so it's a tiny fraction. But they always said that the cases where they don't detect it, it's also because they don't reach the signal to noise that is necessary, so we will never know. So, I mean, this polar stuff, it's interesting, but I think we need more observations before we can rule out that a simple torus model is what we should use to reproduce the infrared spectral energy distribution. So precisely, this is the case. No, this is what we did. I have done a lot of work doing this, trying to reproduce these SEDs with torus models, and in some cases we can reproduce it well with a simple torus model, no polar emission at all. So this is what we get. And in some cases, for example, this is a Cipher 1 galaxy in which they have detected the polar emission with the VLTI, with interferometry. And you can see that there is an excess that the clumpy torus model alone cannot reproduce. So this is the kind of scenario that we face. So this can be produced by the polar dust. In the case of this galaxy, very likely because apparently there is polar dust in the interferometry data. But it could be also reproduced if we include more resilient dust grains in the clumpy models. So, for example, if in the inner wall of the torus you have more graphites, which are more resilient to high temperatures, the sublimation temperature is higher, so they can resist higher temperatures, then you would be able to reproduce this feature. We have ruled out that it's due to host galaxy contamination because we have studied how the emission of this component correlates with the hard X-rays. So we know that this AGN heated dust, so it can be either this polar emission or a different composition needs to be adopted in the model. These are some of the models that include this polar dust. Like I was saying before, the WADA models. So the idea is that you have an inflowing disk of material and an outflowing wind driven by radiation pressure. There are different sets of models. And the idea, for example, this is a comparison between a clumpy torus model only. So this is the parameter space that we cover with the torus alone. This is near infrared to mid-infrared spectral index. Basically, it tells you about the shape of the SED and mid-infrared spectral index. Okay, so we are basically seeing the range of SED shapes that we can accommodate with the model. So this is torus only and torus plus polar dust. So you can see that in this case, we reproduce the case of NGC 3783, which is the SED that I showed you before with the bump that we could not accommodate. So this is the kind of thing we are trying, but like I said, in my opinion, it's too soon to see how important is this polar component to reproduce the observation. And now let's move to ALMA. ALMA is the new stuff that we have regarding torus studies. And like I said, now we have a bunch of AGN observed with the tori result. The first one was NGC 1068, which was observed in cycle 2 by Santiago Garcia Burillo, a close collaborator of mine. And we published the first paper. There was like a race trying to get the first ALMA results published because there is another group led by Jack Gallimore, which published on the same year. They published in the same year, and also by the Japanese group. There were actually duplications of the ALMA observations, so they observed the same target with the same configuration, and the papers were published more or less at the same time. But in this case, Santiago won the race for a few months only. Okay, so this is the inner part of the galaxy. This is the circum-nuclear disk that I was telling you about before. So this is something that we observe in molecular gas. This is a molecular gas reservoir of 200 parsecs in diameter, more or less. This is the position of the AGN that we know from the radio, for example. And this is the ALMA cycle 2 observations in color. The contours correspond to cycle 0 observations, which have a lower angular resolution. And you can see the first thing that we noticed is that the torus is, as expected maybe, is not an isolated structure, but is connected with the galaxy. In particular, is connected with the circumnuclear disk. And this is very interesting. And if we do a zoom of the AGN, so this is the torus that we resolved. This is the ALMA, the beam size. So the torus is resolved. This is dust continuum at 400 microns. So we are looking at the very cold dust in the torus. And this is a little bit of elongation that we see here, but basically the bulk of the torus emission in cold dust is here. And if we see the torus in this case in molecular gas, in CO625, which is high density gas, we see that's even a bit more compact. So the diameter of this torus is about 10 parsecs in size. So very compact in the case of NGC 1068. And this is the gas mass, 10 to the 5 solar masses. And like I said, it's interesting that it's connected with this circumnuclear disk. So this is the first time that we saw this, and it was very, very exciting. And this is new. This is not even published. This is also data from Santiago, Garcia Urillo. In this case from cycle 4, so even better angular resolution. And this is the torus of NGC 1068, again, observed in 3 different transitions, in CO221, CO322, and HCO+. So basically, we are seeing higher densities as we move in this direction, okay? So low density, intermediate, and higher density. And what we find is that the torus is quite large. So we have 2 configurations. So this is the compact configuration to recover the whole torus extent in these transitions. And then this is the longest configuration to be able to see the details of the torus with high angular resolution. So when we look at the total torus extent, something that we see is that as the density increases, the torus decreases. So it becomes large when we go to the low densities, 28 parsecs in diameter. This is quite large, actually, compared with what we expected originally, maybe. This is the ALMA beam in all the images. When we go to high density, it's very similar to what we observe in cycle 2, no? To the torus that we see here in CO65. And when we look at the details of the torus in these 3 transitions, something that we see is that the shape is irregular. It's not an homogeneous, a symmetric thing, but it's lopsided, and actually it gets more lopsided as we go to lower densities. So this was for NGC 1068, and this is very nice. This is work that is in preparation. But now we have formed a collaboration called GATOS, Galactic Activity Torus and Outflow Survey. And so the idea is to observe near AGN with ALMA and with the James Webb to look at the sub-millimeter and infrared counterpart of the torus in a more representative sample of nearby AGN. This is part of the team in a meeting that we had in Winchester a couple of years ago. And we have started applying for ALMA time of a few nearby targets. These are the observations. This is a project also led by Santiago Garcia Urillo, who is our ALMA person. And so, for example, those 2 cipher galaxies, 5506 and 6300, observing CO322, HCO+, and dust continuum. I think it's also at 400 microns. And you can see that we are also finding large tori of 30, 20 parsecs in diameter. Again, large, like in the case of 1068. And this torus is perpendicular to the polar, to the outflow axis. No? Sometimes we detect an outflow in the polar direction, and the torus is perpendicular to it. But notice that in the case of the ALMA data, we are not detecting this polar emission. So we look at the images, and if you look at this, for example, this is a torus. We don't see the strong polar emission that we were talking about in the infrared. So the bulk of the mass of the torus is in the equatorial direction. This polar emission might be important in the infrared, but if we talk about mass, the mass is in the torus. And apparently this is something that also the models reproduce. So interesting times, and need to work simultaneously to see what's going on. This is another paper led by François Combs, published very recently on a sample of lower luminosity AGN. So I was talking about Seyfert before, and these are more like liner-like AGN, so very more low luminosity. Also observed with ALMA in different cycles. They were trying to get this sample of galaxies observed with ALMA. And they are finding also large tori. You can see here the radii of this tori. We go from 10 to even 30 parsecs. So they are also detecting large tori even in low luminosity AGN, which is interesting because it was predicted that at lower luminosities the torus could disappear, or at least we expected it to be smaller than in Seyfert galaxy. but that doesn't seem to be the case, at least for these luminosities. This is also something very interesting. And if we compare with simulations, because I was saying that at the beginning we were a bit surprised that the torus was so large in the ALMA data, but this is really not surprising if we look, for example, at the simulations. This is a model of the torus from the 2008, so 10 years ago. And this is how the torus would look like if we look in the near or mid-infrared. So when we look at the hot dust, so here is where we expect to see very compact tori in the infrared. But if we move to the far infrared or sub-millimeter, like I said before, we are looking at cold dust. And the cold dust, of course, is on larger scales than the hot dust. So we will be talking about the radii that we are observing with ALMA. So not that surprising that we are observing large tori with ALMA. And like I was saying before as well, the torus is connected with the galaxy, is connected with the circum-nuclear disk. So this is again 1068, observing in cycle 0 with ALMA. Here I'm always indicating where the data come from. So this is a star-forming ring of NGC 1068, which is also known because it has a lot of star formation. So this is a star-forming ring. This is the circum-nuclear disk, this CND, the molecular gas reservoir. This is a zoom in CO322 and in CO65, lower density, higher density. Again, the same, larger and smaller, depending on the density we look at. We see that the AGN is not right at the center of the CND, but it's sitting here in this region. And something that Santiago found out from this cycle 0 ALMA data is that the CND itself is outflowing. So he detected outflows in the CND. So the CND is also connected with the rest of the galaxy, and in this case, in the form of outflows. And on smaller scales, when we look at, this is symphony data of the same galaxy of NGC 1068, when they look at the connection between this CND and the AGN, what we see here, the CND and the AGN, from the symphony data, they said that this, they will be observing inflows of gas, no? So these tongues of material would be flowing towards the AGN. And this is something that they, like I said, they were claiming to see in the near infrared when they look at the molecular gas, but this is hot molecular dust, the H2 lines that we observe in the near infrared, as compared to the cold molecular dust that we observe with ALMA. So this is something that Héctor Vives Arias is looking, putting together the ALMA cycle 2 data that we have of NGC 1068. And he's precisely looking at the connection between the CND and the torus to see if these tongues of material that are connecting both of them are inflowing or outflowing material. And it's very complex. It's not straightforward to understand what's going on. But hopefully we will be able to see what is the case for this galaxy. Also, like I said, 1068 was observed by the other group, by the American group in cycle 2, led by Jack Gallimore. They basically found the same results as Santiago. So Santiago concentrated more on the torus structure, on the size of the torus, the kinematics of the torus. And the data by Gallimore et al. Was a little bit deeper than Santiago's. So they were able to study in more detail the gas kinematics in the torus. So something that we all found is that the torus is dominated by rotation. So we see molecular gas rotating. But in addition to this rotating gas, there are non-circular motions that in the case of Gallimore they explain as an outflow. So there is an outflow perpendicular to the plane of the torus. No? So we will have the torus rotating and then an outflow in the perpendicular direction. So this is what we observe in NGC 1068. But for example, in the case of NGC 5643, which is another Cipher-2 galaxy, studied by Almudena Alonso Herrero in a paper that was published last year, So she had the same kind of ALMA observations. This is from cycle, I think it's cycle 3 in this case. So we observed this galaxy. This is a composition of Muse data in blue and green. And this is the ALMA data in red. And this is like a cartoon view of what we see from the observations. So there was an outflow detected from the Muse data in oxygen 3 and also in H alpha, so in ionized gas. But what Almudena found is in the case of this galaxy, where we also resolved the torus, which in this case it's of 26 parsecs in diameter, the torus itself is participating in the outflow. So in the case of this galaxy, we don't see an outflow in ALMA data in the same direction as in the ionized gas, but the torus itself is outflowing. So we find a variety of situations in all nearby AGN that have been observed with ALMA so far. And this is all very exciting. We need to put together all the pieces of the puzzle. Something that we are also seeing is that the closer you get, the more complicated it gets, of course. So in the case of NGC 1068, there are different groups competing, also working on cycle 4 and cycle 5 data and finding opposite results. So publications will come up soon, and we'll have a lot to discuss. So to sum up with this part, we detect very large tori in the sub-millimeter of Cipher galaxy, and the torus get bigger at lower densities. We find that the torus is always dynamically perturbed. It's lopsided, it shows outflows, etc., and is connected with the CND, as I was saying. And some galaxies show polar emission in the infrared that is not detected at the moment in the sub-millimeter. So a lot to be done. Okay, and very briefly, I want to go over, well, very briefly, I don't know, I have been talking for 40 minutes, so, well, I'll try to do it quickly. So I would like to move from the central parsecs of AGN to the inner 2 or 3 kiloparsecs of the galaxy to talk a little bit about outflows. So this is work that is in progress. This is the project I'm now more involved. And let's go back to the slide that I put at the beginning, why we care about AGN feedback, because it's important for galaxy evolution. So we are looking for this negative feedback that quenches star formation and explains, allow the simulations to explain the observed number of massive galaxies. And like I said, we have been looking for this negative feedback, and we found some examples of powerful AGN showing strong outflows that can empty the gas of the galaxy and halt star formation. But these are rare cases. No? In the majority of the AGN that have been observed so far, the effect of this AGN feedback is not as dramatic as we were hoping when we started to look for it. So one controversy that I think is more or less solved by now is the extent of the outflows. The outflows are winds launched by the AGN. When they were first looked in quasars, which are powerful AGN, before we were talking about intermediate or low luminosity AGN, but now we move to quasars, which are high luminosity AGN, because those are the AGN that are expected to have higher impact on their host galaxies. So when people measured the extent of these outflows, of these winds, at the beginning they were reporting very large sizes of 10 to 15 kiloparsecs. And they were claiming that if the outflows were so large, of course they were having a strong impact on the galaxy, and they will be able to empty the gas reservoirs. But apparently, at least some of these works that were based mainly on IFU data did not carefully address the size of the sink. So you have to be careful that you account for the size of your PSF. And if we are looking at quasars at redshift 1, let's say, your PSF is going to be of a few kiloparsecs. So if you don't take that into account, of course you are going to find outflow sizes that are of the size of the galaxy. So apparently this was something that was affecting at least part of these works. And if we look at the more recent literature, where people were more careful in looking at that, I'm not saying that these people were not careful, but it can be the case. So the sizes of the outflows that people are now claiming for quasars are of 1 or 2 kiloparsec in size maximum, sometimes even more compact than that. So this is something that has changed. And also another problem is that when people measure outflow rates, the simulations normally require that the outflow rates have to be approximately between 1 or 10% of the AGN volumetric luminosity to have an impact on the host galaxy, to quench the transformation. And normally people measure much lower outflow rates than that. So this is why at the beginning this was a bit disappointing, I guess. And so we are looking for outflows. So normally in the spectra, what we see when we say that we detect an outflow, what we see is a broader component than the narrow lines that is shifted. Normally we see it blue shifted, because if this is the case, imagine we have a biconical outflow. So one part of the outflow is blue shifted and the other is red shifted. But if we have the galaxy sitting here, then this part of the outflow would be obscure, and we typically see the blue shifted part. But depending on the geometry and orientation of the galaxy, we might see the red shifted part. There are cases in which we see that. But this is the more typical scenario, so we normally look for these kind of lines in our spectra to identify outflows. So perhaps part of the problem that affected the search for negative feedback were that people only look at the ionized phase of the gas. So most of the work done in outflows has been done looking at the oxygen-3 lines in the optical, because it's easier. We have a lot of optical spectra, for example, from Sloan. There are papers published on large samples looking at the oxygen-3 lines, looking for these broad components. I mean, this is great. This is work that has been quite useful. But something that, like I said at the beginning, it's very important to look at different phases to try to understand what's going on. Perhaps we are missing part of the energy budget of the outflow if we don't look, for example, at the molecular gas or at the neutral gas. So something that we have seen for some sources now, for a few galaxies only, that have been observed in different, using different tracers, like molecular, ionized, or neutral gas, is that the characteristics of the outflows change a lot depending on the phase you look at. So we need to look simultaneously for the same galaxy at different gas phases to measure the outflow rates and the energy input and see if perhaps this is what we were missing. Maybe if we concentrate on the ionized gas only and find that it's not doing any damage of the galaxy, perhaps we can find the opposite if we look at other tracers, or if we put all the tracers together. So we need to look at all of that to really assess the impact of the outflows in the host galaxy. So this is a project that we are starting here. This is something that I'm leading now, and we are trying to investigate outflows in a sample of quasar 2s, observing in the near infrared. So the advantage of looking at the near infrared spectrum of nearby quasars is that we observe ionized and molecular lines in the same shot, because we have these H2 lines in the near infrared, so we can compare the outflow properties directly for the same targets. And then the idea is to investigate the impact of this feedback on galaxy processes that are taking place on short time scales as the AGN. So for example, we will look at the star formation and at these molecular gas reservoirs that we were detecting with, seeing with ALMA before, and also at the young stellar population. So this is a huge project that I'm trying to put together, And like I said, I have selected a sample of type 2 quasars that have been observed already with flown, so we have optical spectra for all of them. I like the size of the sample is nearly 50 quasar 2s, and I think this is an ideal sample size because you get enough statistics to derive significant results, but still you have the opportunity to look at the individual properties of the sources, which is something very, very important to understand what's going on. And we have also different morphologies in these targets to see if they have any influence on the feedback and on the star formation of the galaxy. So we are now obtaining observations with EMIR on the GTC. We have a significant part of the sample already observed. So we want to study the outflows and also the stellar populations using the infrared and the optical, and really understand what's going on in terms of feedback in these galaxies. So this is the kind of spectra that we are getting. This is an example of a source that we have observed with EMIR. So this is a typical spectrum that we have. This is the high spectral resolution spectrum, showing different lines, sampling different gas phases. And in the case of this galaxy, we also detect very nice extended Paschen alpha emission. So this is a typical case that we would have observed for these quasars with EMIR. And I think I'm going to skip this because I have talked a lot. So this is the case of for a subset of the sample that we are observing with EMIR. We also have IFU observations, either from Symphony on the VLT or from NIFS in Gemini. This is also work in progress, but we already published an example of these quasars. This is the Teacup galaxy, a very interesting galaxy that is radio quiet, but still has a lot of radio emission. And it's a nice example of how the jet, even in a radio quiet AGN, is driving nuclear outflows, because we see them extended in the same direction as the jet. So this is a very nice example. We did the characterization of the lines in the near infrared, and thanks to the IFU capabilities of Symphony, we get these maps of flux, velocity, and velocity dispersion. So we observe the outflow in the ionized and coronal phases of the gas. We don't detect the outflow in molecular gas, but we observe this circum-nuclear disk that could be the quasar counterpart of the CNDs that we observe in lower luminosity AGN. And to sum up, like I said, it's very important to look at the different gas phases, and we also need to target different samples of AGN when we want to study AGN feedback, like low versus high luminosity AGN, type 1s, type 2s, etc. And the jets, so studying the objects in the radio, it's also very important, because even in radio quiet AGN, like I was saying before, like in the case of the Teacup, we see that these jets may be an influence in driving these nuclear outflows that we see in the optical or in the near infrared. And that's it. Thank you very much.
So thank you, Cristina.
I'm sorry it went too
No,
long.
that's fine. Perfect. Time for questions.
Thanks for your nice talk, Cristina. So it seems that this issue with the outflow, the scale of the outflows, it does seem there seems to be some disagreement between what the simulations want and what the observations are getting, right? There seems to be a disconnect, that you're seeing scales, outflows on scales of a few kiloparsecs, where we really need things on scales of tens of kiloparsecs or more. So,
Well,
I mean, is that a fair comment? I mean,
yeah.
are we facing is this a problem, or do you think it's going to go away as you go deeper?
No, I don't think so. I think that was the most simplistic scenario, no? The easiest thing to find. Well, okay, if we detect outflow of 10 or 20 kiloparsecs, then done. No, we know that it's going to halt star formation. But if this is not the case, as it looks like it's happening, I think that simply the things are more complex. No? So yeah, perhaps we are missing part of information because we are only looking at the oxygen 3 lines. or maybe it's not as fast as we were expecting. No? It's not simply emptying the gas reservoir and that's it. Maybe it's something more continuous. No? Maybe they don't quench star formation immediately, but it's something to that happened in a longer time scale, or in a more slower or not so dramatic way.
Yeah, as a continuation of that question, because it's something that obviously is of our interest, no? If you, perform this project with these new observations and you are expecting to find that you can maybe extend or not, okay, from 1-2 kiloparsec to maybe, we are talking about what is your expectation, and the second thing, this is the first question, the second thing is how you would expect that this to vary over time. If you go with the redshift or something like that. I think this is a key question.
Yeah. Actually, so I'm concentrating in local quasars because this is where we have the angular resolution to look at nuclear outflow and see them in more detail. But of course, we need to compare this with higher redshift because my personal opinion is that most of the harm was done to galaxies at high redshift. So feedback in the local universe, I don't expect to have to be as dramatic as it was, for example, at redshift 5 or 6. The problem is that at redshift 5 or 6, the observations, are not going to tell us a lot because we basically cannot resolve anything. But if we look at, for example, at the papers by Ignacio Martin Navarro, where they are studying you know it very well, they start forming histories of galaxies and can trace them up to this redshift, so when the universe was younger. They are finding that even for non-AGN, apparently AGN feedback is what you need to explain the M-sigma relation, and to explain the star-forming histories that they are finding. And they are finding that the feedback was more important at redshift 5 or 6. But so this is one possibility, okay? This is something that we need to check. But like I was answering to Mike, I think in the local universe, maybe we are not going to find anything dramatic, like I say. I don't expect to find giant outflows. They are going to be compact, of 1 kiloparsec or something like that. But maybe if we measure these outflow properties in the different gas phases and put together the outflow rate that we measure in the different phases, maybe we are going to find that they have more impact than what we get when we only look at the oxygen free line. This is my expectation.
Okay.
Yeah or not, yeah. This is what I hope, but we'll see.
Yeah, so just a quick question. I think you're right that the AGN feedback should be more pronounced at high redshift because it's a mechanism to prevent gas to fall in, and in the local universe you don't have enough. Gas is not falling in massive galaxies anyway. So my question is, some simulations said that in fact you don't need AGN to quench, but in fact it's more a maintenance mode. So a maintenance mode. So you quench because of halo heating or something like that when you reach a threshold. But then AGN is more a mechanism to regulate and maintain and prevent gas to fall in. So in that respect, you won't expect such a big correlation between young stellar populations and outflow, or because the galaxy is already quenched in some sense. So how you can distinguish between these two processes in this study?
So I think the key thing here is the luminosity of the AGN we are talking about. So the maintenance mode, I think, is going to be more important in the dominant population of AGN, which are lower luminosity AGN. So in reality, if, for example, in the local universe, we only have a few quasars. Quasars were more abundant at higher redshift, but in the nearby universe, we have more low luminosity AGN. So I think those are going to be important in terms of the energy budget and maintenance mode. And actually, I think their most recent results are in this direction. But in the case of quasars, it can be different, no? Because we have seen that in some of them there is actually very strong feedback that can impact the star formation, no? So perhaps in general numbers, at least in the local universe, the maintenance mode is more important. But in the case of quasars, it can be more important. And maybe, okay, maybe they are not as relevant in terms of the general population because there are only a few. But I think these local quasars are very interesting because they are laboratories of what we observe at higher redshift, no? At high redshift, it can be more important, the radiative feedback, the feedback that we observe in quasars. And when we observe them in the local universe, because we have them close, we have like one of these quasars put close to us. Yeah, well, okay, but we can, what you lose in that sense, you gain it in the level of detail that you are able to resolve. Yeah. So I think from the point of view of understanding the physics and what's going on, they are very interesting, even though we don't find that the impact on the star formation is as high as it could be at high rate.
So, any other?
What is really the best evidence of torus in terms of geometry? Because what you have shown in general, they are compact sources.
The torus.
Yeah. Apart from 1068, I think, where
no,
there is.
All of them are more or less the same. Yeah.
No, but I mean, the first case you showed was, well, here's the torus. Yeah, but I didn't see a torus. I saw a compact source.
A compact source.
Is the modeling that tells you? I mean, how do you know that it's a torus and it's not, let's say, a disk?
You mean like a torus, like a donut,
a donut,
basically? Well, no. I mean, normally what you observe are disks, no? So, in some cases, for example, in the comms paper, no, here we see a disk. Okay. Yeah. So these are disks, no? Then you study kinematics and everything, but this is a disk basically. But if you look at this, for example, at the comms paper, in some of them they found these more ring shapes in some of the images that they have. But yeah, normally we observe this, rotating this.
Oh, okay, I have a question about the polar emission. You said that most of AGN, you don't see them, but why, how they form?
How they form the polar emission?
Yeah.
Well, according to the models, it's just part of the same outflow that we see on larger scales. So that would be a nuclear, a very compact outflow launched by the AGN, by the radiation. No? So when you put in the models of radiative transfer or whatever in the simulations, you get naturally these fountains of gas and dust.
Okay.
And you observe them both in the gas and in the dust.
Okay, but I'm wondering, could it be because of the agent activity trend? If when the activity is low, and there could be some inflow go to the polar position, then when activity is high, could be.
You mean if it's related to the AGN luminosity?
Yeah, or something about the inflow.
Yeah, well, I mean, actually, it has something to do with that because, for example, in these fountain models by WADA, so they, that one. So the idea is that you have the outflow, and then there is part of the outflow that falls back in the plane and forms the disk. And yeah, this is part of a cycle that might stop if the AGN luminosity decreases. And actually, one problem that these models have originally is that it was difficult to maintain the cycles, no? So they were static. But I think this is more solved in the last models.
So, I think we have to stop here. Okay. I mean, it was enough. Remember that there is coffee in the cafeteria, so we can keep the discussion there. So thank you again, Cristina.
Perdón, es que me emociono, me pongo a hablar. Yo creía que lo iba a hacer más corto.